At 7:02 on the morning of December 7, 1941, two soldiers sat inside a canvas-topped truck on a hilltop called Opana Point, on the northern tip of Oahu, Hawaii. The truck contained the operating equipment for a mobile radar station, a device so new to the United States military that most officers had no idea what it did or why it mattered. The two soldiers, Private Joseph Lockard and Private George Elliott, were supposed to have shut the set down at 7 o'clock. Their shift was over. But Elliott was still learning the equipment, and Lockard was showing him how to read the oscilloscope. At 7:02, the oscilloscope showed something neither of them had ever seen before. A blip, enormous, unmistakable, appeared at the edge of the screen, 136 miles to the north, moving toward Oahu at roughly 3 miles per minute. It was, Lockard would later testify, the largest signal he had ever seen on a radar screen. Elliott wanted to report it. Lockard was less certain. Their duty hours were over and the signal was probably nothing, but Elliott insisted, and Lockard picked up the telephone and called the information center at Fort Shafter. He reached a switchboard operator who put him through to the only officer on duty, Lieutenant Kermit Tyler, who had arrived at his post exactly 1 week earlier. Tyler had almost no understanding of radar. He had no training in evaluating radar plots. He did know that a flight of B-17 bombers was expected from the mainland that morning, and the signal seemed to be coming from roughly the right direction. "Don't worry about it," Tyler told Lockard. The blip on the oscilloscope was not 6 B-17s. It was the first wave of the Imperial Japanese Navy's attack force, 183 aircraft, fighters, bombers, and torpedo planes launched from 6 aircraft carriers 230 miles north of Oahu. They were flying at 10,000 feet in tight formation straight toward Pearl Harbor. Lockard and Elliott watched the blip grow larger for the next 34 minutes until at 7:39 the signal disappeared into ground clutter, the electronic noise generated by the mountains of Oahu itself. The operators had tracked the incoming attack for 37 minutes. They had seen it coming from 136 miles away. They had reported it. Their warning had been dismissed by an officer who did not understand the machine that generated it. At 7:55, the first bombs fell on Battleship Row. The radar worked. The system around it did not. And the story of how America built that radar, how a handful of engineers at a forgotten Army laboratory in New Jersey created an electronic eye that could see over the horizon, and how a nation that possessed this miracle failed to use it, is one of the most consequential tales of industrial engineering in the Second World War. Before radar, the primary means of detecting approaching aircraft was the human ear. This is not a metaphor. In the 1920s and 1930s, the United States Army operated enormous acoustic listening devices, concrete horns some 12 feet across, mounted on swivels, connected to rubber tubes that fed directly into a listener's ears. The operator would rotate the horn until the sound of distant engines was loudest, then read the bearing off a graduated scale. On a quiet night with no wind, these devices could detect a formation of heavy bombers at a range of perhaps 15 miles. On a windy night, or over the ocean, or against fast-moving aircraft, they were nearly useless. The Army also experimented with infrared detection, the idea that the heat of an aircraft engine might be detected at a distance by a sensitive thermal sensor. Colonel William R. Blair, the director of the Signal Corps Laboratories at Fort Monmouth, New Jersey, initiated Project 88 in 1931, titled Position Finding by Means of Light, where light referred to electromagnetic radiation in the broadest sense, including infrared and radio waves. The infrared approach showed some promise in controlled tests, but the signal was too weak at distances greater than about 6 miles. It was not a practical early warning system. What Blair and his engineers needed was a way to see aircraft at distances of 100 miles or more, in darkness, through clouds, in any weather. They needed a technology that did not yet exist in any militarily useful form. They needed radar. The story of American military radar begins not at a defense giant's gleaming research campus, but at a cluster of wooden buildings at Fort Monmouth on the New Jersey coast. The Signal Corps laboratories had been consolidated there in 1930, a Depression-era measure that brought scattered research units under one roof. The entire operation consisted of 5 officers, 12 enlisted men, and 53 civilians. Their budget was minimal. Their equipment was surplus from the First World War. Their mission was everything the Army deemed too obscure or too experimental for anyone else to do: radio, meteorology, wire communications, and the detection of aircraft. Blair was the right man for the job. He held a doctorate in physics. His research focused on the interaction of electromagnetic waves with solid materials, and he was stubborn enough to pursue ideas that the Army's bureaucracy considered fringe science. By 1935, Blair had concluded that the most promising approach to long-range aircraft detection was the use of pulsed radio waves. The concept was elegant. Transmit a short burst of radio energy into the sky. If the pulse strikes a metallic object, an aircraft, a portion of the energy bounces back to a receiver. By measuring the time between the transmitted pulse and the returning echo, you can calculate the distance to the object. By noting the direction the antenna is pointed, you know the bearing. The Americans were not alone in pursuing this idea. Between 1934 and 1939, 8 nations developed pulsed radar systems independently and in great secrecy: the United Kingdom, Germany, the United States, the Soviet Union, Japan, the Netherlands, France, and Italy. The British were the most advanced. By 1938, their Chain Home system was operational, providing continuous radar coverage of the English Channel and the approaches to London. The Germans had developed the Freya and Würzburg radars. The term radar itself, radio detection and ranging, was coined by the United States Signal Corps in 1940. The concept had been demonstrated independently by the Naval Research Laboratory in Washington, where Robert M. Page had detected aircraft at up to 36 miles using pulsed radio signals in 1934 to 1936. Blair was aware of the Navy's work, but the Army and the Navy did not share information easily. In 1935, one of Blair's recent arrivals, Roger B. Colton, convinced him to send an engineer, William D. Hirschberger, to the Naval Research Laboratory to see what they had accomplished. Hirschberger returned with a positive report. Blair found money. He diverted funds from other projects. A research team was organized under Paul E. Watson, a civilian engineer. By late 1936, Watson's group had built a working radar prototype, a 75-watt, 110 MHz transmitter with pulse modulation and a receiver. The frequency was in the VHF range, with a wavelength of about 3 meters. The entire apparatus was mounted on 2 trucks. On December 14, 1936, they tested it near Newark Airport in New Jersey. They aimed the transmitter along the flight path of commercial airliners and listened for echoes. It worked. They detected an aircraft at 7 miles. 7 miles was not 100 miles, but it was a beginning. 5 months later, on May 26, 1937, Blair invited the Secretary of War, Harry H. Woodring, and the Assistant Chief of the Air Corps, Brigadier General Henry Hap Arnold, to Fort Monmouth for a demonstration. The crude radar prototype, still designated by its cover name as a position-finding device, successfully detected an unlighted bomber flying at night. Arnold was impressed. He immediately saw the potential. A long-range version of this device could give the Air Corps advance warning of incoming enemy aircraft. He urged the Signal Corps to develop an early warning radar. This moment, an Air Corps general watching a blip move across an oscilloscope on a spring night in New Jersey would lead directly to the events at Pearl Harbor 4.5 years later. Arnold's enthusiasm translated into funding. A special congressional appropriation of $250,000 was secured. The Signal Corps set to work on 2 parallel systems. The first, designated SCR-268, was a short-range radar for directing anti-aircraft searchlights and gun batteries. It operated at 205 MHz, had a 10-degree beam width, and could detect aircraft at up to 28 miles. The SCR-268 used a ring oscillator circuit with 16 tubes, producing about 75 kilowatts of peak power. It was the Army's first operational radar system, and by May 1939, it had achieved operational readiness after extensive testing at Fort Hancock. Western Electric and Westinghouse engineers were brought in to assist in the development. The second project, which would become the SCR-270, was far more ambitious, a long-range early warning radar designed to detect aircraft at distances of over 100 miles. This was the system that would change everything. But shortly after the demonstration, the Signal Corps received alarming intelligence. German spies were interested in Fort Monmouth. An agent named Gunther Rumrich had actually driven onto the base. A bored guard at the main gate, reading a comic book, waved him through without checking credentials. Rumrich gathered information about the radar research simply by asking officers where the tests were being conducted. He was eventually arrested in February 1938 after attempting to obtain 35 blank American passports for German intelligence. The Signal Corps moved its radar work to Sandy Hook at Fort Hancock, an isolated coast artillery post on a sandbar peninsula jutting into New York Harbor. The new location offered both security and a clear view over water, which was ideal for testing radar against distant targets. The key to making radar work at long range was power. The early prototypes used transmitting tubes that produced about 75 watts of peak power in short pulses. This was sufficient to detect aircraft at a few miles. To reach 100 miles, the transmitter needed far more, at least 100 kilowatts of peak pulsed power in a tube that operated at 106 megahertz. No such tube existed. In October 1938, the Signal Corps awarded a contract to the Westinghouse Electric and Manufacturing Company at its radio division in Baltimore, Maryland, to develop and produce a high-power transmitting tube for the SCR-270 radar. Westinghouse designated the tube WL-530. The Signal Corps assigned it the type number VT-122. It was a water-cooled triode, a vacuum tube with 3 electrodes, cooled by circulating water around the glass envelope to dissipate the enormous heat generated during operation. The tube needed to produce 8 kilowatts of continuous power and 100 kilowatts in short pulses, bursts of radio energy lasting only a few millionths of a second, repeated several hundred times per second. This was the heart of the radar. Without this tube, the SCR-270 was a concept on paper. With it, America would have eyes that could see over the horizon. Westinghouse delivered the first pair of production WL-530 tubes in January 1939. They were incorporated into the first SCR-270 prototype in time for the Army's summer maneuvers of 1939. The radar worked. It detected aircraft at ranges exceeding 100 miles. Under favorable conditions, the antenna sighted on a cliff or high ground overlooking the ocean, it could see aircraft at 150 miles. Maximum consistent range was about 130 miles on a normal day, sufficient to provide roughly 45 minutes of warning against an approaching strike force at typical bomber speeds. The WL-530 was an impressive piece of engineering for its time. The tube was about 18 inches tall, with a glass envelope surrounded by a water jacket for cooling. The water circulated through the RU-3 cooler unit, dissipating the substantial heat generated by the high-power pulses. The plate voltage was 15,000 volts, enough to kill a man instantly if he touched the wrong connection. The power supply, designated RA-33 and later replaced by the Westinghouse RA-39, was built like a piece of industrial equipment. Cast iron, heavy copper bus bars, massive transformer cores. It weighed hundreds of pounds. It was not elegant. It was built to survive being loaded onto a truck, driven over unpaved roads, set up in tropical heat or Arctic cold, and run continuously for days without maintenance. This was field equipment, not laboratory apparatus. The device was crude by any later standard. The antenna was a massive structure, 36 half-wave dipoles arranged in a grid, backed by reflectors, mounted on a folding tower derived from a well drilling derrick that stood 55 feet tall on an 8-foot-wide base. The base was remotely rotatable from the operating truck, allowing the antenna to be steered toward different bearings. The operating frequency was 106 megahertz, a high frequency for 1940 and one that pushed the limits of antenna design. Tuning the antenna was not a precision operation. Westinghouse had a field station at Sandy Hook with a clear view across New York Harbor to 3 large gas storage tanks in Brooklyn. The antenna tower was aimed at the center tank. One man watched the oscilloscope in the operating truck. Another climbed the 55-foot antenna tower with a 4-foot length of 1x2 lumber and banged on the tuning sections, the trombone-shaped adjustable elements, while the man at the scope yelled up whether the signal was getting stronger or weaker. When the return from the center tank was strong and the returns from the side tanks were small, the antenna was considered tuned. This was the state of American radar engineering in 1940. A man with a stick hitting pieces of metal while another man shouted from the ground. It worked. The SCR-270 was a 4-vehicle system. The K-30 operations van contained the radio equipment and the oscilloscope display. The K-31 truck housed a gasoline-fueled power generator, a 76-horsepower engine driving a 31-kilowatt, 3-phase, 60-cycle generator. The K-22B flatbed trailer carried the folding antenna tower, and the K-32 prime mover towed the antenna trailer. A 9-man crew operated the system, a shift chief, 2 oscilloscope operators, 2 plotters, 2 technicians, and 2 electricians. Westinghouse received the production contract for the full SCR-270 and SCR-271 systems in 1940. The SCR-271 was a fixed version, identical electronics, but with a different antenna that provided somewhat better resolution, permanently installed rather than mobile. The Westinghouse Radio Division in Baltimore built the modulator, power supply, transmitter, and other major components. RCA supplied the receiver. Other subcontractors provided the antenna systems, the trucks, and the power generators. Westinghouse ramped up production quickly. By the end of 1941, the company had delivered 108 SCR-270 and SCR-271 units. These were deployed to the most strategically vital and vulnerable positions the United States possessed: the Panama Canal, the Philippines, Hawaii, and other overseas locations. The first SCR-271, serial number 1, was delivered to the Canal Zone and began operation at Fort Sherman on the Atlantic end of the Panama Canal in October 1940. Its first test run detected airliners at 117 miles. A second unit was installed at Fort Grant on Toboga Island at the Pacific end of the canal by December 1940. The Panama Canal, the most important and most vulnerable piece of American infrastructure in the Western Hemisphere, now had radar coverage on both approaches. 6 SCR-270 sets were sent to Hawaii. The deployment of America's first early warning radar to Hawaii in the months before Pearl Harbor should have been one of the great defensive achievements of the war. Instead, it became a case study in how technology fails when the human system around it is unprepared to use it.
The problem was not the hardware. The hardware worked exactly as designed. Private Lockard and Private Elliott detected the incoming Japanese strike force at 136 miles, well within the system's expected performance envelope. They reported it promptly. The problem was that almost nobody in the American military understood what radar could do, what its readings meant, or how to integrate its information into a defense system. The British understood. They had been operating the chain-home radar network since 1938, and they had built an entire command and control infrastructure around it, the Dowding system, named after Air Chief Marshal Hugh Dowding, which fed radar data from coastal stations to a central filter room where the information was plotted, evaluated, and passed to fighter sector controllers who directed interceptors onto incoming threats. This system had saved Britain during the Battle of Britain in 1940. The technology of chain home was not dramatically superior to the SCR-270. What was dramatically superior was the system, the procedures, the training, the doctrine, the command structure that turned raw radar data into tactical decisions. America had none of this. The irony was bitter. The British chain home stations operated at roughly similar frequencies to the SCR-270, between 20 and 50 megahertz, with wavelengths of 6 to 12 meters. The transmitters were more powerful, up to 350 kilowatts peak, but the fundamental technology was not dramatically different. What was dramatically different was everything that surrounded the hardware. The British had practiced air defense exercises for years before the war began. They had trained hundreds of WAAF plotters and filter room operators. They had established standardized reporting procedures. They had built dedicated, hardened telephone lines from every radar station to every sector command. They had tested the system in realistic exercises and corrected its failures before the Luftwaffe arrived to test it for real.
The American military had done almost none of this. The radar sets in Hawaii were treated as training equipment, not operational defense assets. They were operated for only 3 hours each morning. They were staffed by soldiers learning to use them, not by experienced operators integrated into a command network. There was no permanent information center adequately staffed by trained controllers. The entire air defense infrastructure of Hawaii was, as Watson Watt would later observe, organized as though radar were a curiosity rather than a weapon. In 1940, the War Department created the Air Defense Command under Brigadier General James E. Cheney. Hap Arnold, now commanding the Army Air Corps, tasked Cheney with studying the British air defense system and replicating it in America. An air defense school was established at Mitchell Field, New York in April 1941, where operators of the new SCR-270 sets were trained before deployment to the Canal Zone, the Philippines, and Hawaii. But training operators to read an oscilloscope was the easy part. The hard part was training commanders to trust the data and act on it. In Hawaii, the radar sets were operated only from 4 a.m. to 7 a.m., the hours considered most likely for an attack. After 7 o'clock, the sets were shut down. There were no dedicated telephone lines from the radar stations to the information center. There was no practiced procedure for evaluating and acting on radar contacts. The information center at Fort Shafter was not permanently staffed with experienced officers. On the morning of December 7th, Kermit Tyler, a pursuit officer with exactly 1 week's experience at the center, was the sole officer on duty. The radar operators had no access to information about friendly aircraft movements. When Lockard reported the massive incoming signal, Tyler could not cross-reference it against a list of expected flights. He knew vaguely that B-17s were expected from the mainland, and the signal seemed to come from the right general direction. He did not know that 6 B-17s could not possibly produce a blip that large. He did not understand that the radar was showing him something unprecedented. Robert Watson Watt, the father of British radar, was sent to the United States after Pearl Harbor to advise the American military. His report was devastating. He described the general American attitude toward radar as treating it as a freak gadget producing snap observations on targets which may or may not be aircraft. General Gordon P. Saville, Director of Air Defense at Army Air Force Headquarters, read the Watson Watt report and called it a damning indictment of our whole warning service. The technology existed. The warning was given. The system failed. To understand how Westinghouse built America's first radar, it helps to understand what kind of company Westinghouse was. George Westinghouse founded the Westinghouse Electric Company in Pittsburgh, Pennsylvania on January 8, 1886. The company was born in the fiercest technological battle of the 19th century, the War of the Currents, in which Westinghouse championed alternating current against Thomas Edison's direct current. Westinghouse licensed Nikola Tesla's patents for the polyphase AC system in 1888 and then hired Tesla himself. In 1893, Westinghouse lit the World's Columbian Exposition in Chicago with alternating current, proving its safety to the public. In 1895, the company installed the generators at the Adams Power Plant at Niagara Falls, the system that electrified Buffalo, New York, and demonstrated that AC power could be transmitted over long distances. By 1900, Westinghouse employed 50,000 people and had established a formal research and development department in 1906, one of the first corporate R&D labs in America. The company's largest factories were in East Pittsburgh, Pennsylvania, and they manufactured turbines, generators, motors, and switchgear for every phase of the electric power chain, from generation to transmission to distribution. It was this deep expertise in high-power electrical engineering, in vacuum tubes, in transmitters, in the physics of electromagnetic radiation that made Westinghouse the natural choice when the Signal Corps needed someone to build a tube that could generate 100 kilowatts of pulsed power at 106 megahertz. But the SCR-270 was only the beginning of Westinghouse's radar contribution. As early as 1933, Westinghouse electronics engineers at the company's research laboratories in Forest Hills, Pittsburgh, had experimented with radio signals beamed between the Forest Hills campus and the East Pittsburgh works. They observed that road traffic moving between the two facilities interrupted the signals, an early, accidental demonstration of the radar principle. By 1939, the radio division in Baltimore had been selected as the primary manufacturer of the Army's SCR-270 and SCR-271 radar systems. By 1941, the radio division had built 108 units. And then, Japan attacked Pearl Harbor, and the demand for radar exploded. During the war, Westinghouse manufactured more than 8,000 different products for the military, from turbines and ship generators to helmet liners and electric torpedoes. The radio division alone produced over 12,000 GP radio units for the Navy. Employment in the radio division jumped from 500 people in 1939 to 6,000 by 1945. The division's plant area expanded from 60,000 square feet to 925,000 square feet, with facilities not just in Baltimore, but in Lansdowne, Maryland, Sunbury, Pennsylvania, Springfield, Massachusetts, and Mansfield, Ohio. The company produced the Army's first operational jet engine in 1943, the first American-built turbojet. It produced radar systems, airborne radios, power plants for submarines and destroyers, and the first radar installed in a presidential aircraft. Westinghouse engineers contributed to critical breakthroughs in plastics, X-rays, and atomic energy. The company was producing pure uranium by 1941, a capability that would prove strategically important as the Manhattan Project accelerated. But the company's most important wartime contribution may be the one that came earliest, the WL-530 vacuum tube and the SCR-270 radar system that it powered. Because without that tube, without that radar, the United States would have entered the war with no electronic early warning capability at all. The disaster at Pearl Harbor did not discredit radar. It discredited the failure to use radar properly. And the lesson was absorbed with the brutal speed that only a catastrophe can produce. Within hours of the attack, every SCR-270 set on Oahu was placed on round-the-clock operation. New sets were rushed to vulnerable locations around the Pacific. An air defense infrastructure modeled on the British Dowding system was built from scratch. Dedicated telephone lines were installed from radar stations to command centers. Trained officers were assigned to evaluate radar contacts. Information boards, plotting tables, and communication procedures were standardized. In the Philippines, the lesson came too late. Although the Far East Air Force had 5 SCR-270 sets, only 2 were functioning on December 8, 1941, the day Japan attacked the Philippines across the international dateline from Pearl Harbor. One of the operational sets, at Iba, detected the incoming Japanese aircraft, but command disorganization, the same disease that had afflicted Hawaii, meant that the warning was not acted upon. Many American fighters were caught on the ground and destroyed. The largest concentration of B-17s outside the continental United States, 19 aircraft, was destroyed on the ground at Clark Field. The Iba radar set itself was destroyed in the initial attack. The effective striking power of the Far East Air Force was broken in a single day. These failures accelerated the development of radar doctrine, training, and technology at a pace that would have been inconceivable in peacetime. The SCR-270 remained the Army's primary long-range early warning radar throughout the war, but it was supplemented and eventually replaced by newer systems. The most transformative of these were the microwave radars built around the cavity magnetron, the British invention brought to the United States in September 1940 by the Tizard mission. The cavity magnetron operated at a much higher frequency than the SCR-270's 106 MHz, typically at 3 GHz or 10 GHz, which meant it could use a much smaller antenna and achieve much finer resolution. The SCR-270 could tell you that aircraft were approaching from the north at 100 miles. A microwave radar could tell you how many there were. The MIT Radiation Laboratory, established in October 1940 specifically to develop microwave radar, became one of the largest wartime research projects in American history, employing nearly 4,000 people at its peak. Raytheon mass-produced the cavity magnetron at a rate that eventually reached 2,600 per day. The SCR-584, a microwave gun-laying radar developed jointly by the Rad Lab, the Signal Corps, and Bell Telephone Laboratories, could track a single aircraft to within a tenth of a degree, 10 times more accurate than the SCR-268 it replaced. By 1944, American forces deployed radar systems for every conceivable purpose: long-range early warning, fighter direction, anti-aircraft gun laying, naval fire control, submarine detection, navigation, bombing through overcast, and identification of friend or foe. Radar had gone from an experimental curiosity operated by 2 privates on a hilltop to the nervous system of modern warfare. And every one of those systems traced its lineage in some way back to the men at Fort Monmouth, the tubes from Westinghouse, and the 4-truck SCR-270 that had seen the Japanese coming and been ignored. A radar works because of a principle discovered by Heinrich Hertz in 1887. Radio waves reflect off conductive surfaces. The SCR-270 transmitted pulses of radio energy at 106 MHz, a wavelength of approximately 2.85 meters. Each pulse lasted about 10 to 25 microseconds. Between pulses, the transmitter fell silent, and the receiver listened for echoes. The time delay between the transmitted pulse and the received echo, multiplied by the speed of light and divided by 2, because the signal must travel to the target and back, gives the range to the target. At the speed of light, a radio pulse travels approximately 1 nautical mile in 6.18 microseconds. A target at 100 miles produces an echo 1,236 microseconds, about 1.2 milliseconds after the pulse is transmitted. The oscilloscope operator sees a tiny deflection on his screen, displaced from the transmitted pulse by a distance proportional to the range. With practice, operators could estimate range to within a few miles and detect targets reliably at 150 miles under favorable conditions. The SCR-270 had no ability to determine altitude. It provided bearing and range only. The bearing was determined by the direction the antenna was pointed. The operator would sweep the antenna in azimuth until the echo was strongest, then read the bearing from a scale on the antenna base. Range was read from the oscilloscope. Altitude was unknown, a critical limitation that would not be overcome until height-finding radars were developed later in the war. The system's operating frequency of 106 MHz was both its strength and its limitation. At this frequency, the antenna was large. The dipole array was approximately 25 feet wide and 30 feet tall, but the beam was relatively broad, which meant the radar could cover a wide area of sky without precise aiming. This made it well suited for early warning, where the goal was to detect any approaching aircraft at maximum range, regardless of direction. But the broad beam also meant poor angular resolution. The radar could tell you that aircraft were somewhere to the north, but not precisely where. The power supply, a 15 kilovolt, half-ampere rectified DC source, was housed in a unit about 4 feet high, 5 feet wide, and 6 feet deep. The high-voltage connection at the bottom was a cast-finned structure that seated directly onto the insulators on the transformer, eliminating the need for exposed high-voltage leads that could arc or fail in field conditions. This was practical engineering, the kind of design decision that reflects experience with equipment that must work not in a laboratory, but in mud, rain, heat, and salt spray.
The SCR-270 that detected the Pearl Harbor attack survived the war. It is preserved at the Historical Electronics Museum in Linthicum, Maryland, a few miles from the Baltimore facility where Westinghouse built it. The Opana Point radar site on Oahu is now adjacent to the Turtle Bay Resort. A plaque presented by the IEEE commemorates the site where the Signal Corps developed the radar, Westinghouse built it, and privates Lockard and Elliott operated it on the morning that changed the world. The original radar plot, the pencil drawing made by the operators as they tracked the incoming Japanese aircraft, is preserved in the National Archives. Joseph Lockard was promoted after Pearl Harbor and served as a radar instructor for the remainder of the war. George Elliott served in the Pacific. Kermit Tyler, the officer who dismissed their warning, was cleared of wrongdoing by the Roberts Commission, which investigated the Pearl Harbor disaster. The commission concluded that Tyler's error was the result of inadequate training and systemic failures in command, not personal negligence. Tyler served the rest of the war without further controversy and retired as a lieutenant colonel. Colonel William Blair, whose health had failed in 1938 before the SCR-270 was completed, applied for a patent titled Object Locating System in 1945. The patent, based on the pulse echo technique he had proposed in 1935, was challenged by Raytheon, RCA, the United States Navy, and several other companies. The legal battle lasted for decades. Roger Colton, who had convinced Blair to pursue radar in 1935, rose to brigadier general and served as chief of research and engineering at the Signal Corps laboratories. Paul Watson, the civilian engineer who led the team that built the first working prototype, remained at Fort Monmouth throughout the war. The Westinghouse Radio Division continued to expand through the war and into the Cold War, producing increasingly sophisticated radar and electronic warfare systems. The company's East Pittsburgh and Leicester plants, the facilities that had manufactured generators for Niagara Falls in 1895, continued operating until 1988, when they were closed. Westinghouse itself eventually abandoned manufacturing entirely, acquired CBS, and renamed itself the CBS Corporation in 1997. The company that had won the War of the Currents, that had built the first American radar tube, that had manufactured the eyes that saw Pearl Harbor coming, ceased to exist as an industrial enterprise. Here is what the SCR-270 teaches. It teaches that technology is necessary but not sufficient. The finest radar in the world is worthless if the officer receiving the report does not understand what the data means, does not have the authority to act on it, or does not believe it is real. The gap between building a machine and building the system to use that machine, the training, the doctrine, the communication infrastructure, the chain of command, is where catastrophes live. It teaches that warnings are only as good as the people who hear them. Lockard and Elliott did their jobs. They detected the threat. They reported it. The failure was not at the sensor, it was at the decision node. The radar saw the enemy,
The institution could not see what the radar was showing it. It teaches that peacetime development is slow, underfunded, and ignored. The men at Fort Monmouth, Blair, Colton, Watson, Hirschberger, worked for years with minimal budgets, improvised equipment, and institutional indifference. The Army's primary investment in aircraft detection in the 1930s was in sound locators and infrared sensors. Radar was a sideshow, funded with scraps diverted from other projects, until Hap Arnold watched a blip cross an oscilloscope in 1937 and understood what he was seeing. And it teaches that the price of unpreparedness is measured not in dollars, but in lives. 2,403 Americans died at Pearl Harbor. The warning existed. The technology existed. The radar saw the attack coming from 136 miles away, 37 minutes before the first bomb fell. That is enough time to get every fighter on Oahu into the air. That is enough time to disperse the fleet. That is enough time to man the anti-aircraft batteries and sound the general alarm. Enough time to save hundreds, perhaps thousands of lives. The machine was ready. The men who built it, the engineers at Fort Monmouth and the workers at Westinghouse, had done their part. The physics was sound. The tubes were good. The antenna was tuned. The only thing missing was the will to listen. America had no radar in 1940. By 1945, radar was everywhere. In every aircraft, on every ship, at every care field, guiding every gun battery, watching every coastline. The nation that had entered the war with 108 crude sets operated by soldiers who had to bang on the antenna with a stick had become the world's dominant producer of electronic sensing technology. But December 7, 1941, remains. The morning the machine worked and the system failed. The morning two privates on a hilltop saw the war coming, called it in, and were told not to worry about it. The blip on the oscilloscope was real. The attack was real. The dead were real. The only thing that was not real was the confidence that someone, somewhere in the chain, would know what to do with the information. That is the lesson of the SCR-270. It has been learned and forgotten, and learned again in every war since.